Treatment planning capabilities. It is an imaging tool used in many hospitals and imaging centers. Living tissue contains a large amount of water and fat molecules, which contain hydrogen atoms. Magnetic resonance imaging uses the nuclei of these hydrogen atoms, also known as protons, to produce images. MRI can be used to show the position and concentration of the protons in the body corresponding to the position of the various tissues as well as the tissue characteristics. Magnetic resonance imaging requires three main components: the magnet, the gradient coils, and the radio frequency transmit and receive coils. The magnet creates a very strong magnetic field that aligns the protons in the body. The gradient coils change the magnetic field in three planes so that the targeted protons have a different vibration frequency from their surroundings. This allows localization of the protons, which is a necessary step for the generation of the images that an MRI system produces. The RF transmit coil broadcasts a radio frequency signal at a given frequency, matching the magnetic field strength. This matching frequency is known as the resonant frequency. The targeted protons absorb the RF energy. These excited protons produce an RF signal, which is picked up by the RF receive coil. The detected signal provides the data needed to create an image. The main magnetic field, the gradient magnetic field, and the RF energy combine to create detailed images, which make MRI a valuable diagnostic and treatment planning tool. The magnetic field of an MRI system with a superconducting magnet is always on and must always be treated with caution. The main magnetic field is not completely contained within the bore of the magnet. All magnets are surrounded by a magnetic field, represented by the magnetic field lines. The magnetic attraction force varies around the scanner. The force is highest at the opening of the bore. More information regarding the field lines and attraction forces for different field strengths can be found in the technical description. During the site planning, a controlled access area around the MRI system is identified. Outside this area, the static magnetic field does not pose a hazard to the general public. Inside the controlled access area, there is a potential hazard. For most sites, the controlled access corresponds with the examination room. The examination room must be marked with the safety marking plate that includes the warning sign, Strong Magnetic Field. To locate the position of structures within the human body, each MR system applies switched gradient magnetic fields. These switching gradient fields are only active during scanning and do not extend outside the magnet. Every MRI system includes a set of 3 gradient coils. These gradient coils create the gradient magnetic fields used for the spatial encoding of the MR signal. The gradient fields are applied in 3 orthogonal directions to create different imaging planes. The gradient fields are switched on and off during scanning. The performance of the gradients is typically defined by 2 properties: the amplitude of the gradient magnetic field and the slew rate. The slew rate is the speed at which the gradients can reach the required amplitude. The time it takes to reach the required amplitude is called the rise time. Higher slew rates are louder. dB over dt is the ratio between the change in amplitude of the magnetic field, dB, and the time it takes to make that change, dt. dB over dt is measured in Tesla per second, T/s. Implant manufacturers may specify the limiting dB over dt value for scanning an implant. Acoustic noise results from the rapidly switched electrical currents running through the gradient coils. This electromagnetic force is known as the Lorentz force. Since the gradient coils are not free to move, the sudden application of force results in the typical knocking sound during scanning. This knocking sound is louder for scans with high dB over dt values. The sound that is generated can approach acoustic noise levels high enough to cause discomfort or result in tinnitus or hearing damage. The MR system uses a powerful magnet to align the protons in the body. To image protons in the body, an RF signal is broadcast to a targeted area. A large RF transmit and receive coil, the RF body coil, is built into the scanner. The region of interest is placed in the center of the RF body coil, often together with a receive coil. The RF transmit coil broadcasts an RF signal at a given frequency. This is known as the resonance frequency. The targeted protons absorb the RF energy. These excited protons produce an RF signal which is picked up by the RF receive coil. The detected signal provides the data needed to create an image. The closer a receive coil is to the patient and the region of interest, the stronger the detected MR signal, enabling detailed studies. Provided that the appropriate safety precautions, as presented in the instructions for use, are observed and the system is operated by qualified and trained personnel, MRI is a safe modality, producing